Okay, so this is going to be the last half of the lymphatic and immune systems, and I wanted to start off on this slide to clarify. I misspoke at the end of the last recording. Once we bypass that initial barrier, that first line of defense, those solid walls against the external environment, those internal mucosal membranes, as well as the external skin. Once those are breached, we have another line of innate defenses, not the adaptive defense system just yet. We have our internal line of innate defenses, and this will include inflammation and all of the cells and chemicals involved in that local trauma event. So our internal innate defenses are the cells and chemicals involved there. They're still non-specific because it is literally the local area involved. Any of those phagocytes, natural killer cells, present white blood cells, anything around will come to help remove debris, any of those pathogens that have been encountered by those tissues before will be attacked and phagocytized, with waste being removed from that site. Common tissue phagocytes are going to be our neutrophils, our most common white blood cell, moving through the tissues by positive chemotaxis, following those chemtrails, and macrophages, large to eat. These guys are just monocytes out of circulation. Monocytes, if you guys remember, those are our largest white blood cells, period. So macrophage, the word itself, just means large to eat. So our largest white blood cell moving around tissues to engulf pathogens. Both of these cells do this by phagocytosis. Phagocytosis is just where part of the cell membrane from that white blood cell, that immune cell, binds to a pathogen, whether it be a bacterial cell or a viral cell, and essentially pulls it inside just to dissolve it with lysozyme, different degrading chemicals, digestive enzymes, or we can use a respiratory blast where it will have something like peroxide or ammonia, something very high in oxygen or hydrogen, to break apart whatever that pathogen is. Some bacteria are resistant to our enzymes. They develop immunities to us, essentially. Or they just have really, really thick outer coatings, capsules of their own, and try to hide from the immune system. We have other white blood cells out there that coat these sneaky pathogens in opsonin. This is just another protein, a complete protein, so they're large, or antibodies themselves, just on the external surface of whatever that pathogen is. A full coating. This is not an antigen binding to an antibody. This is opsonization, and it leads neutrophils and macrophages to those pathogenic cells. One thing to note is that neutrophils self-destroy, basically. They go through apoptosis once they have attacked and dissolved a pathogen. Macrophages, because they are so large, continue to fight and kill pathogens. Natural killer cells, natural just meaning non-specific. They are not picky. They are part of a really cool group of granular lymphocytes. Lymphocytes are normally agranular entirely, but these super specialized granular lymphocytes do a job for the adaptive defense system mainly, where they react and recognize specific cancer cells and virally infected cells, but they're very picky about what cell they will attack, what antigen they interact with. Our natural killer cells, or NK cells, are part of the innate defense system, which means they're non-specific and not picky about what they will destroy. So they are attacking actively and daily cancerous or virally infected cells within the body before the adaptive defense system even knows that they're there. So these guys eliminate a variety of cells. They're non-specific, so they're not picky. We're looking for cancerous cells, so cells dividing at a really abnormal rate, or something infected. He's a little funky, looks like he's dividing differently than normal. They're not phagocytic. They simply sort of attach to whatever cell it is they're going to destroy and induce apoptosis in that cell. Apoptosis just programs cell death. When this happens, they also secrete potent chemicals that will help enhance inflammation around them. Inflammation, whenever we have damage of any sort, inflammation is always happening. Inflammation is important to prevent the spread of damage. This is also going to prevent the spread of debris and pathogens. It's also going to form a little bit of a block for more debris or pathogens to come into an open wound. Inflammation, that chemical release, alerts the adaptive immune system. And it also sets the stage for repair. It's bringing blood to the site of injury, and it's also pushing those tissues closer together through swelling. Acute inflammation is marked by heat, redness, swelling, and pain. We are going to discuss why each of these things is happening, keeping in mind the physiology of inflammation, why we need it as part of the innate defense system. One of our main guys being released is histamine by these big, nice mast cells over here. Mast cells is another word for monocyte or macrophage. They have a special pattern recognition that will sound the alarm, release some of this histamine. We also have special toll-like receptors that respond to different types of microbe. Once this external protein on a microbe is targeted, is flagged, we release cytokines, which are just another chemical, just another enzyme like histamine to induce inflammation, make those tissues swell. Aside from swelling, we are going to dilate arterioles. This makes capillaries leaky. Arterioles are smallest arteries leading into capillary beds or capillary connections, so they dictate the flow of blood through those capillaries. If we're dilating arterioles, blood flow is going to slow some and be pushed through those capillaries. Blood flow is going to increase because we're wanting to bring it to the site of injury. Said that wrong. We're going to make those capillaries leaky by pushing more blood through them to make sure we can get those clotting proteins and white blood cells into the tissues as well. Because we want those clotting proteins, because we want some of that fibrin and those white blood cells, and we need those capillaries to be leaky for that reason, we also have exudate, which is eventually going to cause edema. This is fluid coming into the tissue in order to bring some of that clotting factor, some of those antibodies to the site of injury. The more fluid that collects, the more there will be swelling of the tissues. The more swelling that there is because of fluid accumulation, the more nerve endings will be pressed on and the more pain is sensed. Pain is also a result from some of the toxic chemicals being released, some of our own body chemicals we've talked about, including histamine, are sort of a little bit caustic in how they interact with other body cells. Anti-inflammatory meds help reduce pain by reducing this swelling. They also reduce the release of those actual inflammatory chemicals by cells. The body also contains interferons and complement proteins. These are just antimicrobial proteins that do specific things to act against viruses or bacteria. Interferons act against virally infected cells, not so much directly against the virally infected cell itself, but they are released by a cell that has been infected by a virus as sort of a flag to other cells, its neighboring cells. He's sending out sort of a call, a chemical call to say, hey, there is a virus in the area, and this helps to protect non-infected cells from allowing that virus to bind to them and take over. Because viruses are so simple They lack the means of reproducing themselves, so their overall goal, pretty much no matter the virus, is to infiltrate a healthy, happy cell and take over the cell machinery. Because they're just RNA, they can get into our plasma membrane, they can get into the cytoplasm of the cell and take over ribosomes and just start recreating viral proteins within our own cells. Interferons, these guys are triggered by healthy cells who have sensed that there are virally infected cells nearby. This helps them to block that protein synthesis so that viral RNA is left exposed and can be broken down. And we have fever as a last innate defense. This is our system entirely, whole body response to elevated body temperature due to infection. It doesn't necessarily even have to be a prolonged infection. Leukocytes and macrophages exposed to any pathogen will release pyrogens. Pyro, what does that sound like? Heat, fire, right? Pyromaniacs really like fire. Pyrogens are just chemicals that are sent through the bloodstream to alert the hypothalamus to make the body hot. The hypothalamus is the body's thermostat. He's going to increase metabolic rates so that the body will warm up, ideally to kill off bacteria. This also stimulates pyrogens themselves, stimulate the liver and spleen to take up more zinc and iron. This is a guess by scientists, but it's assumed that they take up more zinc and iron to reduce bacterial growth. The interesting thing about fevers overall, they can do quite a lot of damage. There's not really a lot of understanding as far as the health mechanism. It does save us, but it seems more caustic in most cases because there's no end. This is almost a positive feedback loop that if you continue to be infected and your body does not take care of it naturally, or you cannot receive treatment to take care of it fully, fever itself could denature proteins, right? Our brain is not happy when it's super, super hot. This leads us to our adaptive defenses when all else fails, right? These are specified responses and must be primed. There must be some sort of initial exposure to a pathogen for our adaptive immune system to take over. There are three important aspects of the adaptive immune system. It needs to be specific. It will be a known target that, again, one of our immune cells has encountered before. It's systemic, so the whole body is going to respond. It's not restricted to the initial area of infection, right? The circulatory system and the lymphatic system are carrying things. This works both ways. Infection can be also spread throughout the body because of this. And it has memory. Once we have encountered a pathogen, we develop those antibodies and keep them and keep producing them to make sure that the next time we are exposed, we have a stronger defense. We're ready to keep the body safe. The two divisions of the adaptive defense system are the humoral immunity and cell-mediated immunity. Humoral immunity is what we think about most often when we think about the immune system. This is antibody-mediated immunity. I think I said meditated earlier, sorry. Mediated immunity. Antibodies produced by our B cells, right? Our B cells are free-floating. They're not directly attacking pathogens. They're producing an army of plasma cells to make nothing but antibody proteins to mark pathogens. These antibodies, as they're being produced, are pushed into lymph fluid as well as the bloodstream and circulate everywhere. Cellular mediated immunity is exactly how it sounds. These are the lymphocytes, the T cells directly attacking pathogens that they have encountered and can identify. Both arms of the adaptive defense system are triggered by antigens, right? Those surface proteins, those surface glycolipids, something on the external of a pathogen. When we talked about adaptive immunological memory, like how we remember pathogens, we're going to talk about primary and secondary responses. Primary, just as it sounds, is the very, very first time a lymphatic cell is exposed to a pathogen. Because of this, mounting an immune response is very slow comparatively. This takes 3 to 6 days to even begin the production of antibodies. Then the production sort of peaks at around 10 days and then stops. The antibody count does not get anywhere near as large as it does during any secondary infection. Secondary immune responses, reinfections by a previously encountered pathogen. This can be the second time or the second 100th time, but it's essentially the same once we've encountered it. Every time we re-encounter it, ideally our immune memory should become stronger. Because of this, the response is so much faster. Within hours, your body will start making that antibody, and within days, the level of antibodies within the blood and lymph fluid is greater by a lot than any of the levels of antibodies during that first primary response. And then during secondary immune responses, that antibody level will stay high and can remain high for weeks to months even. Oh, one more thing. Because they've already encountered this specific antigen, the antibodies themselves also bind to those foreign particles even better than before. They seek it out, they've recognized it, so there's a higher affinity or a higher likelihood that the antibody will bind correctly to that antigen. And active humoral immunity, we can have this naturally or artificially. This is just how we develop those antibodies. We need B cells to encounter an antigen somehow. Natural exposure, this is where you actually get the sickness of some sort, the viral infection, the bacterial infection. Your body fights it off, and then you have those antibodies from it. If we're talking about blood, if you are a Rh negative individual, you can have one transfusion of positive blood type. Once you have had that exposure, though, the secondary immune response would cause agglutination because you'd have developed those antibodies. Artificially acquired humoral immunity, that's going to be our vaccines. And what are vaccines? They're just the components of those pathogens. Most of them are literally the dead pathogen itself or a very, very weakened form of it, but some of them are just the proteins, the caustic proteins from those pathogen components. Vaccines provide two benefits. Obviously, we are getting those antibodies, those immunological marker responses, so that when we do encounter that specific pathogen down the road, we have a built-up immunity to it of some sort. Benefit two, though, is a nice one because we don't have to go through all of the discomfort of contracting the full-blown pathogen usually. This is not to say that vaccines aren't without fault, because there are crazy rare occasions where people do get very sick from them because the pathogen wasn't weakened enough. But the number of those cases is so few and far between, and the number of lives saved every day by vaccines is insanely large. It is important that they continue. There's a huge, huge public health push for children and elderly to get vaccines. And because of that, children and elderly generally do receive a good amount of vaccines. I'm saying this because the statistics for adults dying of entirely preventable infections is quite high. Some 65,000 American adults between the ages of like 30 and I wanted to say 65, but I might be making that up. Middle-aged adults who should know to get vaccines don't as often and can have very serious health problems from completely preventable infections. So interesting tidbit on that. Antibodies, these are the guys that we're making. They're just big fancy proteins. They all have different shapes and they are classified based on these shapes. They do 4 very specific jobs: neutralization, agglutination, precipitation, and complement protein fixation and activation. To make this easier, plan, right? Precipitation, complement fixation, and activation, we're going to cut down to lysing. We'll talk about that in just one second. Agglutination we've already discussed, and neutralization. So plan, P-L-A-N. Neutralization is the most common. It's the simplest defense. This is our lymphocytes attacking and binding to those pathogens, destroying them. Agglutination and precipitation. Agglutination is specific to blood cells, but precipitation is the same sort of scenario in the body tissues with other cells aside from red blood cells. They clump together because of that collection of antibodies with the foreign antigen, making those big clumps easy for phagocytes to find and devour. Oops. Complement fixation and activation. This is just a whole bunch of antibodies collecting on the surface of one single thing. One complement protein will bind, and because of this, it becomes activated and changes shape. Sound familiar? It kind of sounds like clotting, right? One platelet will bind, activate, it will swell, and then call a whole bunch more platelets over. So in this scenario, this complement protein is fixating on the surface of a pathogen. He's activating and calling a whole bunch more antibodies over. They coat the surface and lyse it, completely destroying it. I'm doing things a little bit differently with the questions. So I have both chapter questions, multiple choice and short answer here. But again, I have bolded the important questions that I think from both chapters that should be focused on for the quiz as well as for the future test. I am going to start taking extra credit questions from the list of lecture review questions as well. If you guys have any questions, let me know. Let me know if this video is helpful, and I will see you Monday.